Afterwards. Hello and welcome to our presentation on the use of carbon fiber in developing composite materials for prosthetics. My name is Shreya and these are my teammates, Philip and Skylar. In this presentation, we will provide an introduction to the topic, briefly discussing the significance and objective of using carbon fibers in prosthetics. Next, we will move to the user need, touching on the design requirements based on the physiological conditions of someone who requires prosthetics. Next, we will look at the material selection and manufacturing process. And finally, we will end with the discussion on the economics of carbon fibers and whether they are a feasible option for prosthetics.
To introduce carbon fiber prosthetics, some of the significance behind this is that 2.1 million Americans suffer from limb loss, 1.7 million Americans use prosthetics, 1,558 American military personnel lost limbs from the wars in the Middle East, and 30% suffer from depression, anxiety, or PTSD. So this is a topic with big significance. Some of the complications and challenges that prosthetic users face is that they complain of skin irritation and discomfort when using their current prosthetics. Another thing is that the process of adjusting to the prosthetic limb is lengthy and could be challenging depending on the user. And athletes and more active users need stronger prosthetics, better able to support higher loads and stresses to be able to compete at the highest level. And also some heavier weight people may need stronger prosthetics to be able to support them. So our objectives with the rest of this presentation are to consider an alternative to the current main contributor in the market that is moving from metal to carbon fiber prosthetics, and discuss how carbon fiber prosthetics are manufactured and some of the economics behind it.
Next, we move on to the user needs. The one obvious requirement for a lower limb prosthetic is to be able to support the weight of the user. However, during more intense exercise, such as running, the prosthetic may experience up to 3.3 times the body weight of the user. It is also ideal that the prosthetic mimics the mechanical behavior of the limb it replaces, for example, the leg. The leg exhibits a spring-like behavior which supports the user's center of mass. It is able to store and return mechanical energy, which reduces the need for additional muscular force to generate movements. Prosthetics are designed with the spring-like model in mind with varying spring stiffnesses. A stiffness level can be prescribed by a doctor based on the user's weight and expected activity. Higher stiffnesses assigned for higher body weights and/or higher activity levels. Additionally, it is ideal for the elastic modulus of the prosthetic to match closely to that of bone, the primary load-bearing structure in the body. The modulus and design of the prosthetic determines how much and in what way the prosthetic carries load, and subsequently how the proximal structures carry the remaining load. Abnormal loading in these structures can lead to discomfort in the residual limb and abnormal gait, or potentially even a loss in bone mineral density. For reference, cortical bone has an elastic modulus of 3 to 30 GPa. Prosthetics must also meet requirements outside of physiological needs. The prosthetic is expected to function with desired mechanical properties near room temperature and at atmospheric pressure. The prosthetic may experience varying levels of humidity depending on where the user lives. Amputees typically get prescriptions for prosthetics every 3 to 5 years. Within this time, the user's body and activity levels may have changed, new pain or discomfort may arise, or the prosthetic may just become worn out. The table shows example ranges for pricing of different types of prosthetics. The price can be influenced by amputation level, brand, and performance needs. Prosthetics are typically covered by insurance. However, a patient without insurance may have to pay from under $10,000 or up to tens of thousands of dollars for more advanced prosthetics. It is also important to note that the patient may have to pay for physical therapy as a result of receiving the prosthetic, which may limit how much they are able to afford for the prosthetic itself. In current prosthetic designs, metals are used as a load-bearing structure. Typical choices include aluminum, stainless steel, and titanium. The choice of metal and the size of the prosthetic may be customized to the user's needs. Titanium is a desirable option for several reasons. It has a high strength to weight ratio and is biocompatible. While its elastic modulus is higher than that of bone, it is still closer compared to other biocompatible options. Polymers can also be used for prosthetics, but not as a load-bearing structure. They are typically used for smaller features such as joints, phalanges, or connecting structures. Polymer choices include polyoxymethylene, polyurethane, and polyphenol chloride.
Next, we're going to move on to the materials and manufacturing of the prosthetic. So to do an overview of the manufacturing process, first will be the measurement and design, then the mold will be fabricated, and then it's the preparation of the carbon fiber, then the layup, and then either resin infusion, compression molding, or vacuum bagging, then curing, finishing, and lastly the assembly and fitting. So to go over the measurement and design of the prosthetic, first is assessing the needs of the patient and taking accurate measurements of their residual limb, and this may involve consulting with healthcare professionals such as prosthetists or orthopedic specialists to understand the patient's mobility goals and any anatomical considerations, and this ensures that the prosthetic fits as comfortably and securely as possible. And next, CAD is used to create a 3D model of the prosthetic limb. The CAD model can be customized to accommodate for factors such as the patient's unique anatomy, their activity level, and aesthetic preferences. Designers may incorporate features such as adjustable sockets, ergonomic shapes, and weight-saving structures to optimize comfort and performance of the prosthetic. Then lastly, designing a carbon fiber prosthetic is often an iterative process where the initial CAD model is refined and adjusted based on feedback from the patient and healthcare professionals. And this iterative approach allows designers to fine-tune the design to achieve the best possible fit, function, and appearance. And next is the fabrication of the mold. So once the design is finalized, the next step is to fabricate the mold that will be used to create the carbon fiber prosthetics. And this mold is typically made from a rigid foam material that is easy to shape and carve. And then we will prepare the carbon fiber, and the carbon fiber sheets or rolls are prepared. These sheets are made up of thin carbon fibers bound together with resin. The next step in the process is the layup. So with the mold complete, the next step is to lay the carbon fiber fabric on top of the mold, and then the fabric is bonded to the mold using an epoxy, polyester, or acrylic resin. And this is most commonly done one of two ways. Either compression molding, where pressure is applied to the layers to distribute the resin evenly, or vacuum bagging. So once the carbon fiber fabric has been applied to the mold, it is placed in a vacuum bag and sealed. And then is the curing process. So the entire assembly is placed in an oven or autoclave to cure. And curing involves subjecting the carbon fiber and resin to heat and pressure. And this activates the resin and causes it to harden, forming a rigid structure. Next is the finishing process. So once the carbon prosthetic has cured, it is removed from the vacuum bag and the excess material is trimmed away, and any minor imperfections or defects in the carbon fiber are filled and sanded down to create a smooth finish. And lastly is the assembly and fitting process. So any additional components such as joints, sockets, or padding are added to the prosthetic limb and it is fitted to the patient.
Next, to consider some of the economics of carbon fiber prosthetics. Currently, the total prosthetic market is $1.9 billion, and this is expected to grow at a CAGR of 4.9%, CAGR symbolizing the growth rate. So in 2032, the market is expected to get to $2.93 billion, meaning that there is potential to make a bigger market here and for carbon fiber to have a bigger impact. So the potential market for carbon fiber, currently this is 3% of the total U.S. market, and it's currently reserved mostly for athletes who are willing to spend a higher price for their prosthetic to achieve a better performance. With patient claims of irritation and discomfort, carbon fiber composites can be used to build better, stronger, and lightweight prosthetics, and carbon fiber prosthetics can have longer service lives due to their durability.
So another consideration is the environmental impact. So carbon fiber has the potential to have a heavy effect on the environment because it requires a long and complex manufacturing process. Carbon fiber is also very energy intensive, and it is difficult to recycle and it does not biodegrade. Carbon fiber consumes almost 14 times more energy in its creation compared to steel, and carbon fibers exhibit huge emissions of greenhouse gases. Also, there are no sustainable end-of-life solutions that have been available for carbon fiber. However, on Earth Day in 2022, Carbon Fiber Circular Alliance was launched to support a demonstration project to reuse and realign carbon fibers. So this means that the recycling processes of carbon fibers could be one of the best ways to reduce the environmental impact while meeting global demand for this material in industrial applications.
So the question remains, is carbon fiber a big player in the market? Currently, the answer is possibly, but maybe not. Typically, carbon fiber prosthetics are 10 times the cost compared to metals like titanium. And unless a major breakthrough can be made in the carbon fiber cost or manufacturing, the price is always going to remain much greater. So while most users would prefer to use a carbon fiber prosthetic, many are not able to afford the cost, and typically this cost won't be covered by insurance. So as seen, there's also the environmental concerns to consider. However, with a big breakthrough in the market, carbon fiber prosthetics could become much bigger and end up dominating the market. So thank you for listening to our presentation. Here are the references we used.